We are live right now.
Okay. Good evening, all viewers. Okay, today our session is based on a very important topic, which is the data analysis and regression through R software. And today our eminent speaker is Sujoy Das, who is an eminent researcher of Indian Statistical Institute, Kolkata, and an expert data analyst and statistical methods. He also received gold medal in during his master's program. So now our today's session, it will be a very important and interesting session, and we will be going to learn how data analysis and basically the prediction of data with linear and nonlinear regression are going to be obtained with R software. So good afternoon, Sujay.
Yeah, good
Am I
afternoon.
okay?
Am I audible?
Yes, yes, you're audible. So
Mm,
it's over you.
Okay. So, good evening, guys. This is a quick session on. This is a 1 hour session, if I'm not wrong. 1 hour session on regression, linear regression, mainly on linear regression, and we'll be touching upon a few parts of the non-linear regression. Okay, so to begin with, I will give you a basic introduction of the linear regression, and then we will be discussing those things in R. Okay, so let us first discuss what is a linear regression model. I hope you can see the OneNote for Windows, this tab. You can see this. Yeah. Okay. So the basic linear regression model looks like this. So there is a variable, there is a variable which we want to explain, and we want to explain this variable y on the basis of some predictor variables. Okay, so this variable we want to explain, and we want to explain this on the basis of some predictor variables. Suppose there are n many predictor variables. Suppose a1 x1 plus a2 x2 up to an xn. Okay, so we want to explain this variable on the basis of this n many variables, x1 x2 up to xn. This n many variables we will use to explain this variable. But as you can see, we are trying to explain this variable y with the help of this variable and using a linear model. We are using a model where there are no square terms or cubic terms or multiplication terms. We are only using some linear terms. That is why this is called linear regression model. And as we will not be able to explain all of the variation in y using this model, so there will be some error left after the explanation. So that is why this error comes into picture, because after using this linear model, will not be able to explain the whole variation in y. Suppose this is the amount of variation in y, this whole box. Suppose this and we'll be able to explain this part. The remainder part that we are not being able to explain with the help of this model will go into this error portion. Okay, and the better our model is, the amount of error that remains unexplained will be less and less. Okay, so with betterment of our model, the amount of unexplained part will be less. And there are some assumptions of the model, under which assumptions this model works best. So it is we need to check these assumptions after fitting the model. If those assumptions are checked and verified that they are okay, then we can say our model will work well in any situation. But if some assumptions are violated, then there will be some problem in the future use of the model. It might work in that scenario, but in another scenario it might not work well. So what are the assumptions? The assumptions are the epsilon, that is error, the error part of the model, that follows a normal distribution. I am assuming at this moment that you know what normal distribution is, because this is not in our scope within this time frame to explain what normal distribution is. So I'll be assuming that you know normal distribution. And normal distribution with a fixed mean will be assuming the zero mean and a fixed variance. So zero mean, normal distribution with zero mean and a fixed variance. Okay, this is our first assumption. Assumptions. Okay, and the next assumption is this is this is a the variance is fixed throughout the each data point, right? The variance is fixed throughout each data point. So next comes the second assumption, which is the homoscedasticity assumption. So the errors should be homoscedastic. This error is normally distributed. So all the assumptions are on the error. Why we are taking all the assumptions from the error? Because this part of the model is fixed. Because we all know x1, x2, xn. These are our predictor variables. We have the data on these variables in our hand. We have the data. Okay, but this is random quantity. This is observed but random, and the main random part of this thing is goes into this part, the error part. So error is random. So error is normally distributed. First assumption. Second assumption is error is homoscedastic. What is homoscedasticity? We'll discuss a bit later. Third assumption is errors are autocorrelated. Errors should not be autocorrelated. Errors are not autocorrelated. Okay, there are two E's. And fourth one is there should not be any multicollinearity. There should not be any multicollinearity. So we'll discuss each and every one step by step. So what is about the normality assumption and what is the homoscedasticity? Suppose your data looks like this. Let me give you an example. Where comes this homoscedasticity? Or heteroscedastic means that the variance is not same. Variance is not same over time or over data points. Homoscedasticity means that the variance is same throughout the data point. Suppose this is your how this is your data looks like. This is your observations. So suppose this is your data. This is how your data looks like. Now, if you put a line through this point, okay, this is your linear regression line. But as you can see here, the amount of variance means spread of this data. Spread of this data is throughout more or less unique, more or less same spread of this data. But instead of this, suppose your data looked like this. Okay, so now if you put a linear regression line through this point, but because of this funnel shaped variance, this model, however, your regression line looks good, but it will not explain the data very well because of this increasing amount of variance. So homoscedasticity is an important assumption for your linear regression to work well. So as you can see, this funnel shaped, this is a funnel shaped picture, and your variance keep on increasing over time or over data points. So in this way, in this case, your regression, though your regression line looks good and goes through the center of the data cloud, but it will not work well because of this increasing variance or the not unique variance, not same variance. So homoscedasticity is that the variance is throughout at a certain level like this. You can put a bound over this. It might be that some points goes beyond this bound, but that's okay. But throughout the data point, you will find this kind of trend, and you can put a bound over the data points. So it is not out of bounds. Okay, so this is your homoscedasticity. Autocorrelation means, what is autocorrelation? Autocorrelation means suppose suppose let me explain it this way. Okay, suppose suppose the today the amount of rainfall is 30 millimeter. This is today's scenario, today's case. Okay, yesterday it was 28 millimeter. Previous day it was 27 millimeter. Now, as we all know, whenever we this kind of weather situation, we are working on this weather situation, they are somehow related. That means it is it rarely happens that today it has rained a lot, and then there will get a window where it hasn't rained a bit. Okay, it is a rare scenario. It might happen that the amount of rainfall will increase somehow, and then it will decrease at certain point of time. Okay, so this means that today's data is related with the previous day's data, then it is related with the previous day's data. Now, it cannot happen with the linear regression. Suppose if your errors were like this, as we are discussing the error. So if your error also looks like this, so if your errors looks like this, that today this this, suppose this is data point number 1, this is data point number 2, this is data point number 3, and data point number 4. So error at the data point 1 should not be related in some way with the data point number 2. That should be independent. Okay, so this is the the importance of the autocorrelation assumption. So your error should not be autocorrelated. So if it is autocorrelated, if the errors are autocorrelated, so from previous error point, it is taking some information and it is giving that information onto the second data point, and the second data point is getting third data point is getting some information from the previous data point. So in this way, your error will keep on increasing. Okay, so this is one important assumption to check whenever we were dealing with linear regression as a model. Next we come with the first assumption was the normality assumption. We have already discussed homoscedasticity, we have already discussed autocorrelation, and the two more assumptions that are that we are left with, those are normality assumption and the multicollinearity assumption. What is normality assumption? Normality assumption is that at this moment, I am also assuming you have idea of testing of hypothesis or ANOVA kind of scenario. So here there are several test statistics and tests involved in the linear regression. We'll be discussing those things very briefly. Okay, so in those tests, the tests that were used in this model use highly the normal assumption. So those tests are constructed on the basis of normality assumption. If there were no we could not assume normality, then we could not do those tests. Okay, and we could not fit those linear regression models. So this is one thing to understand. And another thing is that, suppose this is your data, this is your observation. Okay, so this is observation 1, this is observation 2, observation 3, and so on. Now, if at each point we can assume a normal distribution like this with the same mean and same variance, I told you that errors are what? Errors are following normal with mean 0 and variance sigma square. Suppose this is your mean line, 0 line. This is your 0 line. So if you assume a normal distribution is a bell-shaped curve, looks like this. Like this. Okay, so as we know that for normal distribution, within this minus 3 sigma and plus 3 sigma limit, minus 3 sigma and plus 3 sigma limit, the 99% of the data points reside in this limit. So if we can assume the normality, then homoscedasticity assumption is already already established, because you can see that in the normal distribution, what happens within this plus minus 3 sigma line, there resides 99.73% of the data points reside in this. So it is highly impossible to for your data points to go beyond these two limits. Okay, so here in this way you can put a bound on your data, right? And your model will look good, right? And the model assumption will be valid. And the next is the multicollinearity. Multicollinearity is what we will try to understand it in very simple terms. Suppose we are using this kind of thing. We are using this model. We are using y. We are predicting y. Y may be suppose yield. Okay, and we are using variable a1 x1 a2 x2 plus an xn. So here x1 may be what it can be. It can be rainfall, amount of rainfall. It can be workforce. Workforce may be either main worker or female worker. Okay, anything. So if what happens in multicollinearity problem, if suppose we are predicting y with the help of this n many variables, n many predictor variables x1 x2 xn. Now if some of the variables, some of the predictor variables are correlated, suppose among this x1 and x2 are correlated, then what happens? Then what will happen? We are trying to explain the variation in y. Suppose this is the amount of variation in y. Now suppose in this whole variation x1 is explaining this part. This is the part that is x1 is explaining. And x2, because x1 and x2 are correlated, so x2 is explaining this part. So this part is being explained twice, and we are thinking the model is working fine, but model is not working fine. Model, because of this multicollinearity setup, because the x1 x2 are highly correlated, that is why this portion is tangled and this portion is being explained twice. So we must have the variables, we should work with those variables that are not correlated, or those are independent. If there are some variables which are highly correlated on one another, so suppose x1 is explaining this part and x2 is explaining this part, but there will be some portion that will be always be tangled, and we might think that suppose this portion is whole is 100% variation, suppose this is explaining 20% and this portion is say 25%. So we might think that at overall it is 20 plus 25%, that is 45% of the variation is explained by x1 and x2, but it is not true, because in this 45% this part is twice, so we have to deduct this, and it is very, whenever this get tangled up, it is very difficult, or it is perhaps impossible to uh, 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 find them individually. So it is, there is a check, there is a check for multicollinearity. We must check whether the variable we are using to predict y, whether they are correlated or not. If they are correlated, then we must delete them from the model. Okay, so suppose two variables are highly correlated, then we must keep one of them and deduct the another one, or remove another one from the model. So with this introduction, with this basic introduction, we'll start our R coding part, and if there are something more required, we'll discuss it later. Okay, I think you can see the R screen, right? Can you see the R screen? Hello.
Yes, yes, it's visible.
Okay. So here we are using this prestige dataset. Okay, so let us look at the dataset. We'll be using head. What it will do, and in R you must press Control plus Enter to run a line of code. Okay, so this data set looks like this. So here is a uh, what should I say, this is a job status, government administrator, general managers, and their education on the basis of some metric, their income, uh, whether I do not know what this variable is. Then prestige, there it is also a metric depending on something that was calculated. Census and type. Type is the whether they are professional, whether it is a white collar job or something like this. Okay, so this is how the data looks like. So now uh, before now suppose in field, whenever you are working in your company or something like that, you might previously know that which is your predictor variable and which is your response variable. Response variables here is y and predictor is the all other variable, you might know. Then you will be using that model. So you will be using that variable as your predictor and those variable as your response. But if you do not know, suppose you want to analyze the data and you do not know which variable are predictor, so what you can do, you can check with what is the relationship between those variables, the how they are related. They are either they are positively correlated, negatively correlated, or what. So that will be done using this line of code. So we are doing a matrix scatter plot. Okay, we are using a matrix scatter plot on the data, but we are excluding the fifth column. What was the fifth column? Let us check what was the fifth column. Fifth column was the type professor. It is not a numeric variable, that is why we are excluding it from our scatter plot. Okay, so let us run this. Okay, so there is one more thing. So you can check the with this line of code summary, you can get the summary of the summary of the variables in the data set. So let's check out the summary. So if we run this summary, so what we are getting? We are getting that education variable. What are the? So we are getting some basic statistics stuff from for each of the variables. For education variable, we are getting mean value, first quartile value, median value, mean value, third quartile value, and max value. So for the numeric variable, we'll be getting this many characteristics: minimum, maximum, third quartile, fourth quartile, first quartile, then median and mean. And for the qualitative variable, so this type variable is qualitative variable, so it will give us the count of the qualitative variable. So BC is the blue collar job. Blue collar job is there are 44 many blue collar job. Professional are 31, white collar jobs are 23, and NAs are 4. So for qualitative variable, we'll be getting this count of this type of characteristics, and uh, for the numerical variable, we'll be getting this mean, median, mode, and something like this. Okay, so this is one important thing. Now what we are doing, we are creating a new data set. We are creating a new data set, and the data set is prestige, but what we are doing, mm, we are keeping this is by this line of code, what we're trying to say is that we are keeping all the rows, but columns will be 1 to 4 and 6. Okay, suppose if we wanted to retain say five rows, then we had to write that in front of this comma. So we had to write, suppose we want to retain first five rows, then we'll be writing c sorry we'll be writing c 1 to 5. Or suppose we want to retain first five rows and then excluding second to sixth and seventh, and then again we'll be the retaining the next two, suppose 8 to 9. So in this way, what we are trying to say, keep first five rows and then 8th and 9th row. Okay, and so we are interested in all the rows, so we are not keeping it, we are not writing anything here. So that means we want to keep all the rows, but we are not interested in all the columns. So we are interested in what columns? This column: education, income, women, prestige. But we are not interested in census column, but we are interested in what type of job they do. So we are keeping the type column, that is the sixth column, right? So you can see 1 2 3 4, We are excluding the fifth column, but we are keeping the sixth column. That is why we have written C1 to 4, comma 6. Okay. Now let us run this, and then we again look at the summary. Now you can see, so here same thing, but there is only one column is missing, that is your what column? Census column, right? Now uh, we'll run this line of code to check the relationship between the variable. Let us see what happens. So as you can see here, we can see the scatter plot matrix. So this is giving the scatter plot of education versus income. So income is on the x-axis and education is on the y-axis. Similarly, this will give you the scatter plot between the education and women. So in this way, we can get an overview of the relationship between these variables. Okay. Now, as you can see, so this is highly positively correlated. This education and income is highly positively correlated. This is a positive trend line, and it is a sharp incline. Okay, like this is a moderately inclined positively correlated straight line. So education and prestige are, so as your education increases, your prestige also increases. This is a highly sharp, highly peaked line. So education increases, the incomes increases rapidly. With your education income, as education increases, your income increases rapidly. So this is the kind of relationship we get from this kind of, and we get a idea of the relationship between the variables from this kind of plot. So this is a matrix scatter plot. So similar kind of code is a scatter plot matrix. Same thing. So we want to explain what we in the in the data prestige. We want to explain what we want to explain. Let us run this code. So this is your scatter plot matrix. Scatter plot matrix. It is not only giving you. It is not only giving you the trend or the scatter plot. It is also giving you a trend line in the data. This middle line is the trend line. There is a bound. This is a upper bound and lower bound, the trend of that, and also the distribution. The what is the distribution of this data looks like. Now, suppose this is income variable is a positively skewed. If you know what I mean, what is a positively skewed, this is no data, no variable here looks similar to the normal variable. Okay, so but we will not be bothered about that, because these are all predictor variables. If the predictor variables are not normal, that is not of our concern. We will we want to check whether the response variable that we are using, or to be specific, the error in the response variable, after explaining the data with this predictor variable, the remainder part, or the error, whether they are normal or not. But here we can see the predictors are nowhere near to the normal. If they were close to the normal, it will be close to a bell-shaped curve. But you can see the prestige variable, income variable, women, education, no variable are normal. Okay, so this part is over. Now what we are trying to do, we could have we could not have done this, but we are doing this. So what we are doing here, we are changing each variable, and we are creating the variable, we are calculating the variable from the center. That means we are centralizing the data, not we are not standardizing. Standardizing means that we are centralizing as well as scaling. So what is the difference between centralizing and standardizing? Let me explain this to you. Suppose this is the variable x. Okay, this is your variable x. This is your predictor variable x. By centralizing, we mean we are deducting the expectation or the mean of the variable from the data. But if we are saying that we are standardizing the data, then along with this we have to divide it with standard deviation of the data. Okay, but here we are only centralizing the data. We are using this variable and the mean of the variable. Why we are doing this, we will explain it later. We cannot do it also, but sometimes it helps in the explanation of the model. Okay, so for that what we are doing, we are creating the variables education.c. That means c stands for standardized, centralized. You can use anything, it doesn't matter whether what you use here. So we are using the command scale. Okay, and the variable name is, what variable we want to centralize, the variable is education. And education is inside the data set new data. That is, we are writing new data dollar education. That means the fetch the variable education from the new data set. Okay, and center is equal to true and scale is equal to false. I just told you that we are want to centralize the data, but we are not scaling the data. If we had written the scale equal to true, then we would get this variable x minus ex by st of x. But we do not want that. We also only want the centralized variable. Okay, so in this way we are changing all these variable education.c, prestige.c, and women.c. Okay, so here also we have done something. We have binded this variable and we have checked the summary of this after centralizing what these variables looks like, what are the summary looks like. So summary. So summary, as you can see, so as we have centralized the data, that means their center has come to the 0. So the 0 is the new center for this variable. This also becomes 0 for the prestige and for the women. And the previous variables are also there. And along with that, we have got 3 new variables: education.c, prestige.c, and women.c. Okay. So now we will come to our first linear regression model. So how do we create a linear regression model? The model looks like this. So this is our model name. You could have given any name. I am giving, as it is a first linear regression model for this session. That is why I have written mod 1. That means model 1. And the code is LM. L means linear model. Okay, and what is your response variable? Response variable is income. That means you want to predict income, and you want to predict income on the basis of what? You want to predict the income on the basis of these 4 variables: education.c, prestige.c, women.c plus type. So these are your predictor variables. So you are using explaining income on the basis of these 4 variables. And where do we get these variables? This response and predictor, will get these variables in the data, new data. So in the new data set, we'll be getting these variables and we'll be creating a linear model using these variables. So let us run this. Okay, now we cannot see anything. So what has happened and what is the result of this linear regression model? To know that, we need to write summary of mod 1. Let's see what is the summary of mod 1. Okay, the summary is, so your linear regression model looks like this. So this is the intercept part, and this is your value of the education.c. This is prestige.c. This is women.c, and there was only one type variable, but we can see here there are 2 more variables that has been added: the type prof and type white collar. We will explain this later, why this has, from one variable they have created 2 variables, why that has happened. We'll explain this in a bit, in a short period of time. Okay, so I want to know, do you know this, the meaning of this p value? Mr. Ornovo, are you there?
Yes, p-value is, I know what is p-value, but a little bit for our audience, you can
Okay, okay,
explain a
okay,
little bit.
okay. Okay. So, so this model looks like this. So we are explaining income with help of these variables. Okay, so let me explain it once. So we are explaining income. Income is our predictor response or y variable, and we are explaining this with the help of education.c plus what was there, education.c prestige women.c, prestige.c plus women.c plus type something, type 1 plus type 2, so let's say type 1 plus type 2. And there are suppose the coefficient of these variables are a1, a2, a3, a4. These are the coefficients. Suppose a5, right? And we have got the values of these coefficients here. So this is the coefficient for education.c is 116.434. So like this. But here in the background there is a test that is being performed. So what is the test? The test is like this: h naught, whether the null hypothesis a1 is equal to 0 against alternative hypothesis a1 not equal to 0. The second test is h naught, this thing a2 equal to 0 against h1 a2 not equal to 0. So in total there are 5 tests that are running in the background simultaneously. So we are checking whether these coefficients are equivalent to 0 or not. Now suppose if this test is gets accepted, we have to accept this test, the null hypothesis, that means we do not need that variable in our model. If this test gets accepted or the null hypothesis gets accepted, then we do not need this model in the we do not need this variable in our model. So for each test we'll be getting a p-value. So you can see here are how many p-values are there. There are actually
Okay,
6 many.
one question I have.
Yes, say
Yes, please go to the one note.
one note. Yes.
Okay, in income equation, I see there is no intercept point.
Yeah,
So,
there is one. I have omitted that. So
okay, okay,
this
okay, okay.
c plus, say c plus this thing. So let me write it once more. So income is equal to some intercept c plus a1 into prestige dot c plus a2 into what was there, education and women, a2 into education dot c plus a3 into women dot c plus a4 into type some type of first variable plus a5 into type of second. Okay, so these were the this was a model. So what we are getting in the linear regression analysis, after doing linear regression analysis, we are getting the estimates of these values, this coefficient. So if we know the estimates of this coefficient, now we can write the model. Income equal to some say 50 plus 14 to something something, and whatever the value is, we'll be writing those in place of this c, a1, a2, and so on. But it is important to know whether this variable is actually important in our model or not, or whether that variable is explaining or adding to the explanation of the variance of the data. So if that is true, if the so in the background, for each coefficient a test is being done in the background. So first test will be h naught c equal to 0 against, so intercept is 0 against h1 c not equal to 0. Second test will be h naught a1 equal to 0 against h1 a1 not equal to 0, and so on. So in this way 6 tests are being done in the background. And if we can reject this test, we can reject the null hypothesis. That means we can reject the null hypothesis. Then we can only say that variable is important for our model. If we cannot reject the null hypothesis, that means we have to accept the null hypothesis. That means our influence of that variable gets multiplied by 0. Because a1 is 0 in null hypothesis and we are not able to uh, reject the null hypothesis, then what happens, we have to eliminate that variable from our data set. So for each variable we'll be getting a p-value. Okay, but we will not discuss because this is a linear regression class, so we'll not be going into the deeper knowledge of the linear the p-value and so on. But for each test we'll be getting a p-value. So a p-value will be getting, and suppose we want to check, we want to do this testing on the at 5% level. As you, I'm assuming that you know what 5% level, 1% level is. If we are checking our, if we are testing at the 5% level or 1% level, then we'll be comparing this p-value. If we are checking testing at the 5% level, we will be comparing the p-value at with 0.05, and if we are doing the test at the 1% level, then we will be comparing our p-value with 0.01. So if the p-value is greater than 0.05, so if p-value, let me write it here, if p-value is greater than 0.05, then we say we accept the null hypothesis at 5% level. And if it is greater than 0.01, then we say we accept the null hypothesis at 1% level. Right? So if our p-value is greater than 0.05, then we'll be accepting the null hypothesis. That means suppose we are suppose that p-value was corresponding to this test. Now if the p-value for this test is greater than 0.05, then we will have to say that we could not reject the null hypothesis at 5% level. That means for this model, the a1 is 0. That means we are no, the a1, the corresponding variable prestige.c is no longer needed in our model. Now on the basis of this knowledge, let us check the linear regression analysis once again. Now as you can see, for the intercept, what is the p-value? P-value is very small, right? The p-value is smaller than 0.05 as well as it is smaller than 0.01. So from that knowledge, we can say that we are not being able to reject the null. We are not being able to sorry. We are rejecting the null hypothesis. That
Accept the
means
null hypothesis.
no, we are rejecting the null hypothesis.
Rejecting, yes. We are not able to accept the null.
You are not able to accept it. That is not said. We also always said that we cannot reject. We reject and we cannot reject. We do not say in terms of acceptance. Okay, in statistics, we do not say in terms of acceptance. We always say in terms of rejection. That means we either we reject or we fail to reject. So here we are rejecting the null hypothesis, right? Because it is smaller than 0.05 as well as 0.01. So whatever the level of significance you take, that is 5% or 1%, it will be rejected on both levels, right? For the education.c variable, you can see it is very large, right? It is far larger than 0.05 as well as 0.01. So this is not significant for our model, right? So from now on, we'll be omitting this variable from our linear regression analysis. So after, if we want to improve this model, for the next model, we'll be eliminating this model from our data, right? The prestige.c, it is very small, and you can see also here with these stars. Okay, there R has already given these stars here, so you can, from here you can also understand which is significant for our model and which is not. If your p-value is very small, that means it is significant for your model, because you are not being able to if the p-value is very small, that means you are rejecting the null hypothesis. That means this thing is not equal to 0, right? So from
So
now
we
on,
will be accepting where the stars are given. That is, the values
no,
are
no,
very
no,
less.
no. We'll be rejecting. We'll be
Sorry,
rejecting. That
Yes.
means we will be rejecting. That means we will be accepting this one.
No, no, no. Variable. I'm talking about the variable. Means in
Yes,
our model, we will only keep the variables where the stars are given.
where
And
the
rest of
stars
the
are given.
variables, if the p-value is very large, then we will eliminate that variable from our model.
From the next model. If we
Yes, from
whenever
the
we are
next.
improving the model, from the next model we'll be eliminating those variables.
Okay, okay.
Okay. So this is one thing, and then there are something called adjusted R square, and mainly R square and adjusted R square. So the higher the better. So R square is if it is suppose for this model the R square is 0.61. If for the next model after eliminating this variable, this many variables, so here we can see the three variables are not significant. So after removing these variables, if we can see that R square, adjusted R square gets improved or gets higher, maximum value is 1. Okay, so then that model will be better than this one. Okay, so we'll not go into the details of R square or adjusted R square in this session at least. Okay, so this is another check of goodness of fit of the model. If we are comparing between two models, if one has the greater adjusted R square, that model will be preferred over the lower adjusted R square valued model. Okay, so this is another check of goodness of fit of the model. Okay,
Okay, I have another question.
yeah.
Is if suppose the variable what we have eliminated,
Hmm.
and we need that variable into our model.
Hmm.
Okay, then what to do? How can we improve that, or should I make the another model for those variables only? For means second model we have to create for those variables which has been deleted
Can you
from our
explain it,
base model.
more elaborately what you were trying to say?
Means suppose we have here you can see the star except the star are p-values.
Okay.
Okay, that is education. We are eliminating the education
Hmm.
variable.
Hmm.
We are eliminating the types of variable and type WC variables also.
Hmm.
But we need those in
Hmm.
our model.
Hmm.
Then what to do?
Then what you can do, you can check whether the relationship that what we are doing here, we are only using the linear relationship. Suppose our response variable is y, that means here our response variable was income, and the predictors are education.c, prestige.c, so on. Now suppose the education.c is being eliminated from this model on the basis of this linear regression analysis. Now suppose you know that this model, this education.c is important for your data. From prior experience, you have idea that education.c is very important variable for your model. So what you can do, instead of this linear relationship, you can check whether some other relationship will be good for this model or not. Suppose some quadratic relationship or some logarithmic relationship. So suppose y equal to say log education.c. You instead of education.c, you might see that from the relationship between y, you can use the scatter plot to check whether between the relationship between the y and education.c. Suppose you see that there is exponential relationship, then you
Yes,
can
yes,
use
yeah.
logarithmic relationship or the quadratic relationship or the cubic relationship. Understood? So
Yeah, yeah.
it is being rejected on the basis of this assumption that there is no linear relationship between y and education.c. Okay,
Yeah.
I think I have answered your question.
Yes, 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 yes.
Okay, so there are too many things to discuss, so I'll be skipping some few things here and there. So oh, one more thing that was important but that got rejected in our that got here. As you can see, there was a variable called type, right? There was a variable called type, but whenever the linear regression is being done, you get two more variables instead of type. You are getting what variable? Type prof and type of white collar, right? Can you do you know what why we are getting two more variables instead of one? Because there were only one qualitative variable type, and type had
Because there were two types which was not in numeric form. One is WC and one is I
no,
think
there were
prof.
three types.
Okay,
There were
three types.
three types: prof, professional, blue collar, and white collar. But instead of those three types, we are only getting two types. These are called dummy variables. Okay, whenever we are getting an indicator variable kind of thing, or a numeric or a qualitative variable, R by default create this. You can also do it by yourself, but if you do not mention anything, R by default create this kind of dummy variable. What are these dummy variable? Let me explain it and shortly. So what it is doing, suppose here the variable was type, right? And in this type there was professional, blue collar and white collar, three types of three kind of jobs: professional, blue collar and white collar. So how to incorporate this info in the linear regression? Because if y equal to something, you are writing income is a numeric variable, prestige is a numeric variable. Now how do you quantify this thing? So in order to quantify this thing, r from this r by default create two more variables. Okay, what is this two variable? This two variable is, say here r is creating type prof and type of wcis, right? Yeah, type wc. So it is by default creating two more variables. From type it is creating two more variables. So what will be the so this is blue color, this is white color. Now type prof will get what? Type prof will get 1 for the professional, blue color it will get 0, and white color it will get 0. And type white collar will get 0 for the professional, 0 for the blue collar, and 1 for the white collar. So in this way, from this it is quantifying it into these two variables. Why instead of three it is doing two variables? Because if you also keep the type of blue collar, then what will be this? This will be 0 1 0. And then if you consider this is what, 1 1 1, right? And then this and these three are becomes dependent. These are no longer independent. So instead of 3 it is only keeping 2. And why it is keeping 2? What will be the explanation of this variable? The explanation of this variable will be like this. Suppose your model looks like this: income is equal to some 50 into 50 into type prof plus some minus 20 into type wc, because there are two variables in the model, type prof and type wc, but one is missing, the type of blue collar. So what will be the explanation of this two variable? The explanation will be like this: if type of professional increases by 1 unit, that means the if instead of blue collar you get a professional job, your income is going to increase by 50 unit. So it is always comparing with the missing variable. Missing variable is, missing status is blue collar here. Here also missing status is blue collar, right? Because professional is also there, white collar is also there. The only missing thing is blue collar. It has been omitted. So it is always comparing with the blue collar. So instead of blue collar, if you find a professional, their salary with 1 unit increase here, their salary will get increased by 50 units. Here also, if you get a white collar instead of a blue collar, your income is going to decrease by 20 units. Okay, is it clear? I guess so, because
Yes, yes. There are some question from audience.
yeah,
One question is what adjusted R square value signifies?
right.
What should be its value of our model?
Adjusted R square is the let me explain it. Adjusted R square is this. So R square is this. R square, there is something called R square, as you have seen. I think you have seen in the screen, R screen. There is something called multiple R square, and then there was something called adjusted R square, right? So R square is, whenever suppose we are explaining y is our income with the help of x1, then R square will be giving you the correlation between y and x1. That means the amount of variation y that is being explained by x1. So it is a positive quantity, right? It is a positive quantity. Then if we use with x1, we use x2 as well, then it will give what? it will give first correlation between y and x1, then correlation between y comma x2, and so on, right? So it will keep on increasing whenever you are adding a variable to your model, however small their contribution might be. Suppose after adding 5 variables, once you have added 5 many variables, then suppose the 6th variable is not that important, but that will be not be reflected with r square. But adjusted r square, they are doing some adjustment with the degrees of freedom. Here I want to do not want to go into the deeper details of the what is degrees of freedom, but there are some adjustment done on the r square value on the basis of the degrees of freedom of these variables, and because of that we can get the actual contribution of that variable. So sometimes what happens, if we find the r square value, suppose the fifth we are using 5 variables, we'll be seeing the r1 with each inclusion of each variable, the r square value is going up, going up, and going up. But if we calculate the r square adjusted r square value, the value will always go up, but the rate of growth will keep on decreasing. Like suppose, say for x1, it increased by this many. So after x2, this is this, x3, this. Then after this, the contribution is like this. So we can discard those variables from the model and keep where there is a sufficient change in the model because of those variables. I think I have answered your question. If not, then so r square,
Yes.
adjusted r square is a uh, modified version of the r square, where you can get the actual, what should I say, actual contribution of the variable on the model. Okay.
Okay. Another question is there, can we compute the missing data or values?
Yeah, why you can? Why not? What do you mean by missing data? If there is missing data, you can find NA in the and you can check for each variable whether there is a NA or not. Is.na, you can type this command is.na, or which, there is something called which command, which is.na in those variable. You can check for those. You can find those rows where there are missing values. Finding missing value is not but dealing with those missing value is a different ball game altogether. But finding missing value is not something very tricky. Okay, you can write a symbol. You can find type in Google and you can find several codes to find missing values. But dealing with missing value is a different ball game altogether. Okay, and there is
Okay, he's also asking that will it affect in R square
what will affect in R square.
the missing values?
If there is a missing value, then we must deal it with first before doing this analysis. Okay, suppose there are several methods of dealing with missing value. Suppose the missing value is very small in quantity. Suppose there are only, suppose we have 1,000 many rows, and on in which there are 5 to 10 rows. Then and after checking that, we see that these rows are not that important, then we will simply omit those rows before doing this analysis. And if it is not possible, suppose we cannot delete it altogether, then what we can do, we can impute those missing values. There are several ways of imputing those missing values, and there is a whole lot of literature on that. Okay, and there are several kinds of missing values: missing at random, missing not at random, missing completely at random. This kind of and we have to check those kind of missingness and treat them accordingly before doing this analysis. Because if there is a missing value, there might be some problems. Okay, this kind of analysis might not work. So we have to deal with missing values first, then we will have to run this regression model. Is there any more question?
Any question from any audience? Okay, I think the questions are, uh, yes, there are no more questions.
Hmm. So do I carry on, Nick?
Yes, 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 you can.
So there is one more important thing to check for the model, for the goodness of fit of the model, is the outlier. If there is outlier, then your model might work very badly. Okay. Let me check whether I've used those. Okay, now before doing that, I will be showing you how to use the non-linear regression in this linear regression framework. You can use the non-linear regression in the linear regression framework. Okay. As I had shown you previously that prestige.c was not significant for that model, right? Now instead of prestige.c, suppose we want to also use the square of prestige.c, the quadratic of prestige.c. How to incorporate that in our model along with prestige.c? We have to write I of prestige.c square. We cannot just write prestige.c square. We have to write I means indicator of prestige.c square. So in this way we can incorporate our quadratic terms in our model. So here, as you can clearly see, this is a non-linear regression because our responses has become log of income, and we are predicting that using these components prestige.c and then quadratic of prestige.c and women.c. Let's again run this model and check the summary, and let's look at the summary. Now as you can see that here all are significant. Here, because here the response has changed, right? And the response has changed. The prestige.c, this is this is completely significant, and this is significant to some level. This quadratic term of prestige.c is significant to some level. How much it is significant? It is significant at 5% level, but it is not significant as 1% level, because as you can see it is larger than 0.01 but it is smaller than 0.05. So if it as it is smaller than 0.05, so it is significant at 5% level, but it is not significant as 1% level. So in this way we can carry out, simply by writing this kind of codes, we can carry out nonlinear regression in this linear regression framework. Okay. Now moving on. Now we'll be finding the residuals, because I told you that we want to check the model assumptions, right? I told you that the assumptions of the models are, first one is normality assumption, next one is your autocorrelation assumption, then there is multicollinearity, there is homoscedasticity assumption, and all are important assumptions. So we must check those after fitting those model. Why after fitting those model? Because after fitting those model we will be getting the residuals, because before fitting those model we will not be getting the residual, and the assumptions are all on the residuals. So after fitting those model we will be getting the residuals, and we will be getting the residuals like this, and we are storing it inside a variable called res. So our model is mod4, the new model, the last model is mod4, right? So we are using that mod4 dollar residuals will fetch the residuals in the model, the residual variable in the model, this will fetch that, right? And this will give us the fitted value of the model. This is giving us what? This is giving us this part. This fit val is giving us this part. Fit val is giving us this part. This part is giving us by fit val, and this part is residual. So unexplained part and explained part. This is our explained part of the model, and this is our explained part explained by the model, and this is the part that is not being explained by the model. Okay, so this is residual and this is the fitted value. So for the normality test, the package is called NOR test, and there are several tests: Anderson-Darling test, Kramer-von Mises test, Shapiro-Wilk test, Pearson test, the QQ plot. Several tests are there. We will only be discussing that one, two tests, maybe say Anderson-Darling test, and we will give you the hint of what QQ plot is. Okay, so here the null hypothesis is errors are normal, against alternative is error are not normal. So p value should not be greater than alpha level. This is very important. Alpha level means 0.05 or 0.01, whatever significance level you are using. So let's run this test first, then I will discuss this. So first we are running Anderson-Darling test. Let's look at the p value. So look at the p value is Any idea what will be the conclusion from this test? Whether we are accepting the null hypothesis or rejecting the null hypothesis, here p-value is very small. P-value is very small means we are rejecting the null
Rejecting
hypothesis.
null hypothesis.
So rejection of null hypothesis means the error are not normal, right? Same we'll find from the CVM, that is Kramer-von Mises test, Pearson's test, Shapiro-Wilk test. So there are some books that you can study, or you can find it on internet as well. Now let us move towards the QQ plot. So for QQ plot, we will be using two lines of code simultaneously, QQ norm and QQ line. We'll be running these two lines simultaneously, and we are running it on the residual variable. That means your out error variable. Okay, now if it was normal, then we would have found out that all the ideal situation would be all the points would fall on the line, or if there are variation, the variation would be very small. But here we can see a band of points is on the line, but then there is a huge deviation from the line, from the below in the below part of the line as well, and in the above part of the line as well. So if it was a normally distributed variable, the error were normally distributed, then ideally we would have all the points falling on the line or very close to the line. So from QQ plot also we can make sure that this variable is not normal, this error variable is not normal. So normality assumption is not satisfied. Next, come to the homoscedasticity assumption. I have already told you what is homoscedasticity and why that is important. I don't know whether I have explained it properly, but in this short period of time, this much can happen. So we'll be using for that, we'll be using, there are two tests, Brioche-Pagan test and Cook-Wisberg test. So here we'll be running one test, that is your Brioche-Pagan test. The Brioche-Pagan test, the null hypothesis error are homoscedastic against the alternative hypothesis not homoscedastic. So if the model has to run well, then we must accept the null hypothesis, or we should be able to reject the null hypothesis, alternative hypothesis, right? So we must accept the null hypothesis in order to for the model to work well, right? So let's run this Brioche-Pagan test. So can you tell me what will be the from the p-value, what will be the decision whether it is errors are homoscedastic or not, as a
This p-value, it is
very small.
95%, I think. Uh, Means level of significance. It is
It is
means
smaller than 0.01 as well as smaller than 0.05,
yes.
right? So if it is smaller, then that means we have to reject the null hypothesis.
Reject, both cases. Reject.
Reject the null hypothesis. That means the errors are not homoscedastic, right? No, sorry. Yeah, right. We have to reject the null hypothesis. That means errors are not homoscedastic. So this assumption is also violated, right? Next, coming to the multicollinearity assumption. I told you what multicollinearity is. Now, let me give you an idea of what multicollinearity is, formula-wise. So multicollinearity is like this. Multicollinearity, for the suppose for each predictor variable will be getting a multicollinearity value. So VIF, so variance, multicollinearity is measured by a quantity called VIF, or variance inflation factor. Okay, so VIF for the variable j, the formula is like this: 1 by 1 minus rj square. Okay, this is the formula. So variable inflation factor for the variable j. So this looks like this. So what it tells us Rj square is what? Rj square is correlation between y and rj, keeping all other variables fixed. So we are not taking into consideration all other variables. That means the effect of all other variables has been omitted from these two variables. So this is giving exact contribution of xj, exact contribution of xj on y. This is giving the exact contribution of xj on y. So now if it now suppose if rj goes higher, what happens? If rj goes higher, what happens? Then 1 minus rj square goes down, right? And as a whole, this goes higher, right? Understood?
Yes, yes.
Hmm. So what happens? So sorry. Yeah. So we'll be keeping those very yeah. So there is a specific value generally used in the literature. If VIF is greater than 10, then we must say that that variable is highly there is multicollinearity for this variable, and we must omit that variable from our model. Okay, we must omit that variable, but as far as I know, in industry they do not use this much high bound. They use generally 3. It depends that they use 3, 4, 3.5, and so on. It varies from company to company. Generally in literature it has been said that if VIF value is greater than 10, we must omit that variable, and that variable is causing too much multicollinearity, or that variable is highly dependent on other variables, so we must remove that variable. Now let's check the VIF values here. The VIF value is this is the VIF, and for this you need to use a package called car. You need to, I have already used it here, the install.packages car, right? And after that install.packages command, you need to write library to car, and inside this car package you will find this function VIF. So let us run this. So as we can see, for each variable, the variable that has been used in this model 4, the prestige.c, the square of prestige.c, and the women, all for all this, this value is very small. Okay, so these are not causing the VIF. These are not causing the VIF, right? These are not causing multicollinearity. If it is small, if it is greater than 10, then this is causing serious problem. Uh, as far as literature is concerned. And then we'll come to on the last but not the least, we'll come to the autocorrelation assumption. The autocorrelation assumptions are, or errors are not autocorrelated, and each one is autocorrelated. So in order for our model to work well, we must accept the null hypothesis, because the null hypothesis H naught, errors are not autocorrelated, and that is our ideal scenario. So let us do this. The test is called Darwin-Watson test, and the command is dw test, and we are doing this on model 4. Okay, so can you tell me uh, what will be the decision on the basis of this test? As the p-value is large, that means p-value is greater than 0.01 as well as greater than 0.05. That means we have to accept the null hypothesis, that we are failing to reject the null hypothesis, right? That means we are accepting the null hypothesis. That means errors are not autocorrelated. So for this model, there is only there are two assumptions are satisfied, that is their errors are not autocorrelated and there is no multicollinearity present in the data, but two assumptions are violated. So this model is not good as long as linear regression is concerned. Okay, so we can, there is scope for improving the model. If there is a normality issue, then we can change some variable to make it normal. There are several but normality is only happens in the laboratory, but in the real world you will not get any normal data, so you have to work your way out of this kind of situation. And last but not the least, there are outliers. Outliers are very important. Uh, this is the one thing that we'll be going to discuss. Will be Now we are going to discuss this outlier points and what why outlier affects our data. Let's understand that first. Now suppose this is your response variable y, and this is your predictor variable x1 or x, maybe x. Suppose this is your the relationship, this is the points, this is how the point looks like, this is the data cloud. The relationship between y and x, as we can see clearly, there is a positively correlated trend line that will go from the center of the data cloud. Now suppose some for some y and x1, so a value, there is something, a value here. If for this data set there is a value here, then what it will do, it will affect the gradient of this line. Now the gradient of this line is like this is the gradient of the line, right? Now as this point is far apart from this data cloud, then what it will do, it will pull the linear regression, because the model has to satisfy this data set point as well. Then what it will do, it will pull this line towards this. So though your ideal line would have been this, but because of this point your model will be like this. Okay, so this is the drawback of a outlier point. Outlier means this is lying very far from the rest of the data cloud, and it is affecting your model very poorly. Okay, so some cases, as you have already mentioned, that if we find that it is important for our data, then there are some ways of bypassing it. But generally what we do, we remove this from our data. We generally remove this from our data and then do the analysis, because most of the data points will be satisfied by this line, but because of this line, the line of the fit will become poor, because this point will pull the line towards itself. Okay, so we need to check whether there are outliers or not, and if we found the outliers, generally what we do, the natural remedy is to omit those data points and then do the analysis once again. So there are several kinds of residuals in the literature: studentized residual, R student, then DF fit, DF beta, Cook's distance. There are several. We'll be discussing two, three, maybe say studentized residual. So let's check for the studentized residual. This is the studentized residual, and we do not know what these values mean. But here, as we can see, that I have given a condition here, that find those rows where the studentized residual is greater than 3. So what I have written, that in the new data set, find those rows. That is why I have rows in the rate in the rows section, and I have left the column section as it is. That means I want all the columns for these rows, but I want those rows for which studentized residual of model 4 is greater than 3. Okay, so this is giving us the studentized residual value, but we are not interested in each and every value, but we are interested in those rows where the studentized residual is greater than 3. That means if we can find those rows, we can omit those rows. So let's look at this. So here we can see the 0 rows. So there are no such rows for which the studentized residual is greater than 3. Now let's check the R student. R student is for the model 4. Command is R student simple. Again we are getting several values, 0.47, whatever it is, but we are interested in the cutoff is 2. If some for some data point or data row, if the student R student value is greater than 2, then that value will be considered as outlier and we have to remove that. Let's look at that, whether we can find such rows or not. Here we can find 2 rows. So these 2 rows are such rows where our student values are greater than 2. So from our whenever we are improving our model, we'll be omitting these rows from the data, and then we'll do our further analysis. They are similar. This is Cook's distance, and Cook's distance, same Cook's distance of model 4, and the outer up the cutoff is 1. If some for some rows the Cook's distance is greater than 1, then those points will be considered as outliers, and so on. And last but not the least, whenever you have done your analysis, completed your analysis by fixing all these problems, suppose you have fitted the linear regression and you have checked all these assumptions, and you are satisfied with, then what you need to do, you need to check the minimum absolute percent error. Okay, though this is not actually a fixed code. You can find this code yourself. The formula I can write, the formula is like this: mean absolute percent error. Mean absolute percent error. Okay, so mean absolute percent error is what? So this is your, so first let's write error. Error is what? This is your observed value, and this is your estimated value. Estimated value is what? Say this is yi, and we have estimated it using what? A1 x1 plus A2 x2 and so on, plus some epsilon I. This part is the estimated part. So this part is yi hat. So whenever we are uh, doing this yi minus yi hat, that means we are bringing this on the left side, then what we are left with in the right side, we are left with the error. So the estimate of the error is the observed minus the fitted value. This, then percent error, right? Absolute percent error. This is mean absolute percent error. So first we have written the error, then absolute percentage. Absolute percentage, how we can find it? So this is the absolute part comes, then the percent, for percent we have to write like this: yi into 100%, right? And then we need to find the mean of this. Mean of this, how can we find? Some I equal to 1 to n, we need to run it, do the summation for n many values if there are n many values, and then we need to take the average, right? So this is the formula for mean absolute percent error. So this is your ultimate goodness of fit of the model. So maximum value is uh, maximum value is 100. So if higher the better. If you're sorry, lower the better. This is a mean absolute percent error. Okay, so the
Lord.
lower the better.
Okay, I think there is another thing which is SMAPI.
Sorry,
SMAPI.
SMAPI.
MAPI and SMAPI, yes.
Oh, so can you tell me the full form of that? SMAPI.
Symmetric it is.
Symmetric.
Yes, yes. MAPI is this, just a symmetric word is added.
Symmetric. Symmetric. I haven't heard of this term, symmetric map.
Okay, okay.
Okay,
Okay,
I will
there are
check.
some from audience, some questions are there.
Hmm.
One student is saying, I'm not from this background, so can you please just explain that how regression is important in approximating any method, means importance before approximating any methodology. I think she is going to ask that what is the application of this regression and how, where we can use the regression, in which
Hmm.
scenario,
Hmm.
what kind of prediction.
Hmm.
Can you please explain?
Hmm. The usefulness of regression is this: suppose you have a data set. Suppose you have a data set. Say, as I have started with this example, yield, and it depends on, we know, the amount of land plus rainfall and so on. Now, suppose you did not use any. Suppose if we can use a linear regression model for this, suppose we are doing a scatter plot on yield on the basis of rainfall. We know that generally rainfall positively affects the yield. Not always, but if there is too much rainfall, the yield will be not be that much. But if it is a adequate amount of rainfall, then yield will be very good. So we can assume that there is a positive kind of relationship. Right. Now suppose we have a data, and on the basis of that we have fitted a linear regression model. Now what we can do for the future, we can use this model to predict on the basis of the rainfall. We can predict the what will the amount of yield that year. Suppose that year the rainfall was like this. Rainfall was here. Here was the rainfall for that year. Now we know from the previous model, because we have already fitted that model, the yield will be somewhere around here. Now we can plan accordingly on the basis of that information, that how much storage space we require, but and so on and so forth. But if we have no idea, but we do not use this information to build this kind of model, so then what we can do, we can suppose the yield is going to as far as regression is concerned, suppose for that year, on the basis of that much of rainfall, the yield is suppose going to be 50 metric ton, but we have only space for 25 metric ton. We have not modified our storage space. Then so what can happen, some of the yield can be get wasted. Okay, so this kind of things to predict, to predict this kind of things, we can use the linear regression. There are several other usages as well.
Okay, another question. Uh, I think this question is not related to this session, but the question is in K-mean clustering,
Hmm.
how we can find which column elements are under which cluster after finding the optimized number of cluster using R.
Sorry, how many, which columns?
Saying that in K-mean clustering,
Hmm.
how we can find which column elements
Hmm.
are under which cluster
Hmm.
after finding the optimized number of cluster using R.
There is a, you can use this which command. We can simply use this huge which command. If you know how to use that, you can simply use that and you can find those, but this is beyond the scope of this session and we cannot show it here. But you I my suggestion for you would be that you can simply use which command.
Okay, yes, this is not beyond the scope of this session. However, we will be discussing this classifications, data classifications in next lectures in other day. Okay, any question from audience? Any other question? Okay, no question from the audience.
Okay, so I think
I think,
I have done my part.
okay,
So
okay.
if no more questions are there, then I think we can
Yeah,
stop
yeah.
this session, right?
Yes, yes. Okay, thank you very much. I thank Mr. Sujoy. He's an eminent researcher. Okay, for this very beautiful session. Okay, now over to Aishwarya, please.
Hi, Shujai.
Hello, Shri.
How are you?
Yeah, I'm fine.
Yeah. Thank you for accepting our invitation and thank you for delivering such a wonderful session using R.
Thank
And
you, thank you for inviting me as well.
yeah, thank you. And those who are watching this video, hopefully they will also get to realize that what is the importance of our software, because we have so many other competitive softwares like MATLAB, Python, right? Excel also we can do regression, but we can choose our software over other one, right? So thank you for delivering this wonderful session. Thank you for your valuable time.
Hmm.
So Sujai, I would like to know that how was your experience in this session, to be here in this session?
Yeah, it was quite good because no such interruption was there. It was quite smooth for me.
Okay, okay. Thank you. We'll if some of our student want to connect with you, so is it okay with you?
Connect how? How they will want to connect?
Through
Through email?
mail or something?
Yeah, yeah, yeah. It is okay with me.
Okay, okay. Fine. Then we have any other questions? Okay, we don't have any other question. Thank you, Shujai, for your valuable time. Thank you so much.
Thank you, thank you. So I'm leaving the session, right?
Yeah, yeah. Thank you. Okay.
Thank you, thank you.
The attendance is
Okay,
available.
the attendance sheet is available in the YouTube comment box. Okay, and please, those who have attended the session, please fill the feedback form and also fill the attendance. Okay, after filling the attendance, all will be getting the certificate for joining the session. And thank you for being with us, and thank you for watching the session.